Hi, everybody. So, welcome to today's meeting for UWI ChemSoc. I'm Nadisha, the president. Today, we'll be doing pectin extraction and we'll be using lemons. So, we're going to be showing you guys what the process would look like. We have some oranges that we're going to use to show you guys what the process would look like. But we are using lemons for today's experiment. So the first part of the experiment is really boiling the albedo of the lemon or of the citrus that you're using. So that's the step that we're at right now. So we are going to be boiling for a while. Um, so I'm going to show you guys where we're at with that. And of course, as usual, we're going to go over the theory of the whole process as well as have questions at the end of the meeting. So this is where we're at. We are, as I said, we are boiling the albedo at this time. But we have a setup here with oranges. We're going to show you guys what the process looks like. Tiffany is here. So she's making up some sodium hydroxide for us to use. So yeah, that's where we're at right now. So while this is boiling and doing all that, I'm going to give it a little stir. Make sure everything mix up. There. So we're going to be boiling this for, when did we start boiling? 220, I think. Somewhere around there, 215 or 220, somewhere around there. So we should be boiling for around an hour. We may cut that to 40 to 45 minutes. So in the meantime, we're going to look at the theory on pectin, of course, what it is, what it's used for, the applications, etc. And then we'll come back to the process. So, well, the first part of the process would be preparation of the albedo. So the albedo is this white part of the citrus. So you can find it on limes, lemons, oranges, grapefruit, tangerine, etc. This white part here. So you would thinly peel the oranges if you're using oranges, whatever you're using. And then you would use a grater to get the white parts off. Once you get the albedo, then that is a part that we would boil in order to get the pectin out of it. So we're going to look at the theory in depth now while that is boiling. All right, so first we're going to look at pectin and what exactly it is, and then we're going to look at the structure of pectin and its uses and applications, etc. All right, so pectin are structural polysaccharides that we find in plant cell walls. They cement the cellulose network and assist with water movement in the cell walls. So you can hydrolyze this structure in the plant cell walls to give pectin, which is very useful to food processors, as it is often used in products like jam, etc. So the pectin is usually extracted as pectic acid and then precipitated as calcium pectate. The exact structure of pectin varies based on the plant source, as well as the amount of pectin would vary based on the plant source as well. So pectin consists of mainly of D-galactoronic acid, which is linked by 14 bonds. So this is a structure that we have on screen of what pectin looks like. So it also contains heteropolymer, rhamno, galacturonan, and a number of neutral sugars, including D-glucose, D-galactose, L-arabinose, and D-xylose, occupying the side chain. So if you look at the structure of pectin itself, you're going to see the main chain, which is in yellow, of the D-galacturonic acid. That's the main chain in yellow right there, going straight across. That is the main part of the pectin. Then we have in, let me see, in L, we have rhamno-AD galacturonan. We also have D-glucose as a neutral sugar. We have D-galactose, L-arabinose, and the D-xylose. So D-xylose, for example, is in blue, the bright royal blue. So you can see towards the center of the structure. And to the right, there is one unit of D-xylose. L-arabinose is the aquamarine color. It's a 5-carbon sugar. So that light blue color, you see it mainly on the left, attached to the D-galactose side chains. Some of it is also attached to the L-rhamnose. And a few units, 3 units, are to the right of the chain of the structure. So these are some of the main sugars. You can see the D-galactose in green, the bright green right there. Those are the main sugars. And then you have a few other sugars that are attached that are minor. So those parts occupy the side chain, but your main component is the D-galactorinic acid. The functional properties of pectin. So pectin has several functional properties, and these are influenced by first the source of pectin. So whether you get your pectin from oranges, lemons, limes, tangerine, grapefruits, you can also get it from apples. So it depends on the source of the pectin. You have different pectins that are used for different purposes based on where you get them or where you source them. So the method of extraction also influences the functional properties of pectin as well as the conditions of your extraction. So in your extraction, the conditions would be your extraction time, that's the main condition. That is, for example, how long we boil the pectin can determine how much pectin you get out of it. The solid, whether the pectin is used solid or liquid, the temperature of the pectin, types of reagents used, as well as the pH of the extraction. So uses and applications of pectin. The major or main application of pectin is that it's a textural ingredient in food systems. So it's used in many food items. For example, jams, jellies, pastries, marmalades, etc. It's also used in cosmetics and personal care products. And we find that in the pharmaceutical industry, it is used in the formulation of control release matrix tablets. For example, it can be used as a carrier material in colon target drug delivery. So essentially, the outer part of the tablet can be made of pectin, the outer layer of the tablet, and it will just break down when you ingest the medication. The multifunctional properties of pectin is what allows it to be valuable in applications in food industry. So you find that it is often used as a thickener or stabilizer or an emulsifier, kind of to hold solutions together to make a solution or a food item thicker. Even something like milk, it can be added to make it thicker, especially when you're making like dairy products where you need a thick and creamy mixture. And it's obviously used as stabilizers and emulsifiers. Pectin can form a structural network and a viscoelastic solution. And so it is widely used in when you're making your jellies, marmalades, and jam. So these things, you kind of use it from a very liquidy mixture, you would say, or solution. It's almost as if when you're adding cornstarch to something, when you add the cornstarch and it gets thicker, it's the same thing. You're adding the pectin to thicken solution. So something like a jelly consistency that you may find in your pastries, like your donuts or your tarts, marmalades, jams, etc., that you even buy at the supermarket. All of those can contain pectin. The different properties of pectin, depending on the source or its processing, we know lead to specific applications. So apple pectin, which apple can be used for pectin, it is darker and it has the property of being more viscous in solution. So the solution will become more a lot more thicker when you add apopectin to it, as opposed to citrus pectin, which is lighter. So the apopectin is usually more suitable for pastries and making fillings, as I said, for like tarts or donuts or anything like that, that jelly that you see in it and in your pastries. So the citrus pectin is a lot lighter, so it's not as thick, it's not as viscous, and it's more suited for texturizing jams and confectionery jellies. So we already talked about uses and applications of pectin. So here we see being used in marmalades, in your jams, in your jellies, in the pharmaceutical industry, being used as an outer coating. This is the apopectin that is being used as an outer coating. We're seeing here where it's added to your jellies and jams, as well as your confectionery jellies. The third picture, where you see the bowl of pectin, and that little thing beside the spoon to the right is a confectionery jelly. All right, so for pectin, commercial sources of pectin usually or mainly come from citrus. So we talked about oranges, lemons, limes, tangerine, grapefruit, especially grapefruit and lemons that have a large amount of pectin. You also have apple pomace, not our Otaiti apple, of course. So traditionally, apple pomace and citrus peels are really good sources of pectin. So as we showed you previously, you would thinly peel the citrus fruit. So you just want to get the green or yellow part off, and that white part is what you would grate and use for the pectin extraction. The citrus is usually preferred to apple because it has a very high content of pectin. So 25 to 35% of, of pectin is in the citrus, and it has a really good color to it. Color. So commercial pectin, as I said, is extracted from the peel, specifically the albedo, which is that white part of the fruit. So 85.5% of commercial pectin comes from your citrus peels, and then 14% from apple pomace, and then we have 0.5% coming from your sugar beet pulp. So it's usually done conventionally and in the commercial space. It is done by acid extraction at a pH of 1.5 to 3, which is pretty acidic. And heating techniques are usually carried out 60 to 100 degrees for several hours. So we can see on the left, the citrus pectin is lighter in color. Sometimes it is almost white. It's almost a white powder. The apopectin is slightly darker, so it's brownish in color. to the gelation of pectin, meaning when pectin becomes a gel, it does so one in the presence of calcium ions, which is why we say we extract it as pectic acid and then you precipitate it as bound to calcium ions. So when you add it in the presence of calcium ions, it will become gel-like, kind of like gelatin in a way. Also, if you add sugar, it will also become a gel. So this is because your sugar is causing dehydration of the pectin, because it will be competing with the pectin for water by hydrogen bond. Because remember we said that the pectin is able to bond to a large amount of water. So if we add some sugar into the solution, then it's going to compete with the pectin for water, and so it will dehydrate. It will also become a gel in the presence of acid, which is the point of using acidic conditions commercially, which we said is 1.2 to 3 pH, to allow it to become a gel. So the acid suppresses ionization so that there is less repulsion, and so that the pectin can become, or the pectin structure can become closer together or repel each other less. So the gels form a 3D network and bind to a large amount of water. So for pectin gel, when it is formed, the properties of it is dependent on the degree of polymerization. That is the degree of polymerization of the pectin structure. So if we have more polymerization, meaning we have more units being added to the structure, then we expect to have a thicker gel. The composition of the side chains, so depending on what the side chains of the pectin is composed of, then that will determine how well it bonds, how well the different structures bond to each other, and how thick the gel, the pectin gel, will be. Cross-linking of molecules. So you will have hydrogen bonding as well as salt bridges being formed in solution. So the cross-linking of these molecules also affect how thick the gel will become, or the property of the gel. The degree of methoxylation, meaning the amount of methoxy groups available, is also going to affect the properties of the gel, if we get a thin gel or a thick and viscous gel. All right, so to the procedure now, which we would have started. So we first weighed about 50 grams of sample. We had 59.1 grams of sample into a beaker. And then we add 400 mils of deionized or distilled water and boil for an hour. And after an hour, we'll transfer the contents to a 500 ml flask and make up the volume of distilled water. So we're going to do that after we finish boiling and filtering this mixture as well into the blood flask. So update on where we're at. We're still boiling. So a lot of the liquid has boiled off. Let me show you guys where we're at now. So a lot of the liquid has boiled off, as you can see. So in about 5 minutes, we're going to filter it into this 500 ml bulk flask, and then we're going to add some sodium hydroxide to it. So we've made up 10 ml, 20 ml of sodium hydroxide that we're going to add to this. After we filter, add to the bulk flask and all of that, then we will be adding the sodium hydroxide, which is the base. So that's where we're at with this. Think we can start filter? No. All right, so we are going to start the filtration. Let me see this one. So we're going to filter into this 500 ml bulk flask. And to add a filter paper. Let me take this off so we can hold. Let me get this off. We're going to filter this. Hot. Oh, so yeah, like lemon tea or whatever, or lime leaf tea. Just stir it out. Oh. Way up and decanter. Yes.
Never use a Pectin to check it. Oh, you know what Pectin look like. You know what Pectin. Oh.
It is hot, you know. Jesus. Oh, Jesus. It gets hot.
But on
My
Pectin are
Lord. So guys, some of the albedo got into the vol flask. So we're just decanting the liquid part of it off, and then we'll add it back to the vol flask. Ouch, I keep forgetting this thing is hot. So, yeah, man. Yeah, man. But man, I don't want it right now. Let's rinse this out. And then I'm going to add back this thing. Really smell like tea. Let me see. Exactly, just need some sugar. Some good tea. Strong tea. Boom. Let me get rid of this. So we're going to make this up with distilled water to the 500 ml mark, and then we're going to pipette out 100 ml of the solution into a beaker, add 100 ml of water to it, and then we add 10 ml of sodium hydroxide. You finished? So we're going to get some more distilled water to make it up. The mark is around here. So we're going to get some more distilled water. The mark is up here, so we're going to make it up to that. And then we're going to pipette out 100 ml of the solution. We may do a more than 100, you know. I feel like doing more than 100. But when we pipette 100 ml, we're going to add 100 ml of water to that. And then we're going to add 10 ml of sodium hydroxide. So after we do that, we're actually going to allow it to stand overnight. So I'll have to come back to the lab tomorrow to finish this. We're going to cover the beaker with a watch glass, leave it overnight, and then tomorrow we are going to finish the procedure. So I'll have to video that for you guys tomorrow so you can see what it is. Oh, cover. All right, guys. So we're going to get a cover for the bowl flask, and then we're going to mix. Jesus. No? I'm not good enough. No. Okay. So we're gonna get a flask cover and then we mix. So let's look at the rest of the procedure and start our questions before we start the pipetting for today. All right, so we had talked about the first part of the procedure where we weigh out our albedo, then we add our distilled water. We add we add our distilled water and boil for 1 hour, which we cut that short to about 40 minutes. And then we're going to transfer that to 500 ml bulk flask, which we did, and made it up with deionized water. It does say to filter the solution afterwards, but we just filtered it before so we can go faster. So for the second half of the procedure, so what we're going to do now is to pipette 100 ml of the solution into a beaker, add 100 ml of water to it, and 10 ml of potassium hydroxide solution. And that is what we're going to allow to stand overnight. So in the morning or tomorrow afternoon, we'll be adding 50 ml of 1 molar acetic acid, allow it to stand for 5 minutes, slowly add 25 ml of 0.5 molar calcium chloride, and let that stand for an hour. And then we are going to dry our filter paper, cool it in a desiccator, and wait. Then we're going to heat the solution, filter it through the weighted filter paper, and thoroughly wash the filter paper with deionized water. And then we test with nitric acid. So what is on the filter paper is going to be the pectin. So we're going to transfer that to our oven and dry it for 30 hours. So this is a long process. So what we're going to do up to adding the sodium hydroxide and allow it to sit overnight. And when I'm back tomorrow, I will do the addition of the acetic acid, the calcium chloride, and all of that good stuff, and then drying it in the oven. So we're going to pipette into a beaker now. We'll probably do 2 batches. Yeah, I think that's a good idea. Do 2 or 3 batches. We can do 5 batches to be honest, but we can do 2 or 3 batches, and then so that we can have 3 sheets of pectin, 3 to 5 sheets of pectin. So we're going to do the pipetting now. Let me get the beaker. So we're going to pipette. All right, so we're going to pipette 100 mils of this solution. See? Must be 100. This is a 20 mil ticket. Let's have to do this 5 times. This is so tiny. Alright. No, I hate this ticket. But no. Not the ticket, the ticket filler, I should say. Oh, finally. That's 20. But the ticket filler I'm saying, Carla. Hmm? 40 mils. That's all. Hmm? Time. Four. 60. 80. Oh my God. And then 100. Hmm? Yeah. 100. Woo! And then 100 of water. And then we're going to do 10 mils of 1 molar of sodium hydroxide. Bless the Lord. The 100 mils of water. Oh, never mind. Forget it. Oh, never mind. We can make it. There we go. 100 mils, 100 mils of water. Father Jesus. And then we need 10 mils. What's in this? Acetic acid? Yes. Yeah. Yeah. Alright. Alright, so we're going to add 100 mils of water to it, like so, and then 10 mils of sodium hydroxide. So I'm gonna rinse this measurement cylinder to do that. So they had in some acetic acid. Alright, great. Still feel like you have acetic acid on it. Rinse it some more. Alright, so we're going to put the, you know what, let me use this just because that did have an acetic acid. I'm gonna have to neutralize it. Then 10 ml. Look like urine. And then I'm that's just annoying. Mix, mix, mix. Then we're going to cover it with a washcloth overnight. And then this is what we're going to use for the extraction. So we're going to make a second batch, but in that time, we will be looking at questions for you guys. So question time. So we've mixed what? 10 mils of the solution with 10 mils of water. 100 mils of the solution with 100 mils of water and 10 mils of sodium hydroxide. So we're going to make a second batch. But it's time for questions now. So let's go. Is it have a cover for this? All right, so the first question is what type of carbohydrate is pectin? Is it a disaccharide, polysaccharide, monosaccharide, or oligosaccharide? Let's see the answers. Let's see who was paying attention. Answers, what type of carbohydrate is pectin? All right, sorry about that, guys. So I'm seeing answers B, B, and A. Correct answer is polysaccharide. So Jophine gets that correct. So Jophine gets the point for that question. So on to question 2. So this next question is, what part of the fruit is used for pectin extraction? And yes, you must be specific. What part of the fruit is used for pectin extraction? I've said this word so many times, I don't even know. What time I say it is the lab start. What part of the fruit? What is the name of it? I see the flesh. I see the skin. Any other answers? The skin, the white part. That is not a scientific name. The peel. That is also not that is not the answer. I'm so sorry. Jophine, the albedo. Thank you. So Jophine gets that answer correct. The answer is albedo. The white part of it. And you can't say I never said that because I said it so many times I can't even count. It's not the pith. The pith is like the middle, like in cherries, the middle part of the cherry is the pith. So it's not the pith, it's the albedo. So let's go to the next question, guys. Justine gets those 2 points so far. What is the most common application of pectin? What is the most common application of pectin? What is it most commonly used for? And yes, I said this a number of times. So let me see the answers. What's the most common application? And this is 2 points enough, people. I see as a thickener, textural ingredient. Jophine, I look like copy and paste. But I look like copy and paste, so. But you are correct. It's a textural ingredient. It is indeed a textural ingredient. So thickener is not necessarily specific as an application. Application is as a textural ingredient. It could be used as a textural ingredient as a thickener, as well as in other ways. So let's go to the next question. Now, I understand how now make just take the whole of the time. That's crazy. Next question is all of the following are conditions of extraction except, what is the exception? We can use which is the exception? All of them are conditions of extraction except. Finish. I come back tomorrow. We finish it.
Finish the experiment?
Yeah. All right, let me see. I'm looking at that. So I'm seeing answer C as the state of the source. I am seeing B, temperature. Guys, it's the conditions of the experiment. All of the following are conditions except. I am seeing temperatures an answer. I am seeing extraction time. I am seeing method of extraction. And the correct answer is method of extraction. And that was by Geneva. We had the correct answer. So the method of the extraction is not a condition. Just how you do the extraction. Tomorrow. Huh? Yeah. Yeah. So yes, the answer is D. Let's move on to the next question. That was question 5. So Josephine has 4 points or 5 points, and Peneva just got 1. So the next question is citrus pectin is preferred to apopectin for pastries and fillings. Is that true or false? Is citrus pectin preferred to apopectin for fillings and pastries? I am seeing the answer is true. I am seeing the answer is false. But which is it? All right, so next question. I hope you guys are hearing me still. All right, so the question is gel properties of pectin are dependent on which of the following? So is it the degree of polymerization, the pH of the acid used, the formation of cross-links, or the composition of the side chain? So the gel properties, so whether or not you get a thin or viscous gel, low or high viscosity, is it dependent on the degree of polymerization, the pH of the acid that is used, the formation of cross-links, or the composition of the side chains of the pectin structure? All right, so I'm seeing degree of polymerization. I think the question, I think it should have except on it. This question seems strange. The properties of the gel, it should have except, guys, so you can change your answer. So the gel properties are dependent on the following except. If you're adding a new answer, add it in all caps. If you're saying over your answer, please add it in all caps. All right, guys, so the answer is B. It is the pH of the acid that is used. So the pH of the acid is not, it is not a gel property. It doesn't affect the gel property. The gel property doesn't depend on that. It depends, the pH is rather a condition of the experiment. So the gel property is, however, dependent on degree of polymerization, composition of the side chains, as well as formation of cross links. So I think Mikhail would have gotten that answer correct, if I'm saying correctly. So we're going to go to the next question. So for this question, it says about what percentage of commercial pectin is made from citrus. So we talked about commercial pectin being made from citrus, from sugar beet, and from apple. So what percentage is made from citrus? Is it 75%, 85%, 85.5%, or 95.5%? Which is the answer? And let's see who has the correct answer. All right, so I'm seeing answer C. Any more answers? All right, so the answer is C. So the first person to have gotten that correct would have been Miguel. So Miguel gets that point. The answer is 85.5%. You get an extra point if you tell me what percentage of pectin is made using sugar beet. You get an extra point if you tell me what percentage of pectin is made using sugar beet. Anybody can tell me that? Can anyone tell me that? I am seeing 0.5%. I'm seeing 25. I'm seeing 0.5. Any other answers? All right, so the answer is 0.5% of pectin is made from sugar beet. So Andre actually gets that correct. It is 0.5%. So he gets that extra point that I was giving away. So let's move to the next question. So this question is, why does pectin gel in the presence of sugar? And this is 2 points in a pip. So you have to actually explain to me, why does pectin gel in the presence of sugar? You have to give me a proper explanation. If I add sugar to the pectin, why does it become gel-like? Kind of like when you add cornstarch to something. Causes dehydration of pectin when it competes with water through hydrogen bonding. What causes dehydration? I have no idea what you're talking about. Andre says sugar competes with pectin for water. Sugar causes dehydration of pectin. That sounds like a 1 point answer. A lot of words, but worth 1 point. There are 3 key things that you need to say. Okay, Jophine says sugar causes dehydration. Dehydration of what, Jophine? So if I eat some sugar, I will become dehydrated? This is what you're saying? Any other answers? Any other answers? I'm giving away points to people. Literally giving them away. Sugar causes dehydration of pectin when it competes with water by hydrogen bonding. No, no. No, 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 no. In the presence of calcium ions, sugar causes dehydration. I will not be accepting. I will not be accepting Mikhail's answer because that is a copy and paste. That is a copy and paste directly from my PowerPoint. I will not be accepting that answer. Anybody else? I know exactly what I type now. So if you copy it, me know. Let me read what Joffine says. If Joffine can see the error in what she said. Joffine says sugar causes dehydration of the pectin when it competes with water by hydrogen bonding. Joffine, please read over that sentence. It's not giving what it's supposed to give. Andre tells me that sugar competes with pectin for water. Sugar causes dehydration of pectin. And there's something very key that is missing from those two statements, right? So I need somebody to give me a complete statement if you need to get the 2 points. Mikkel doesn't get to submit another answer because he's cheating. There we go. Sugar causes dehydration of pectin when it competes for water by hydrogen bonding. I hope Joffin see our error now. Joffin said the pectin competes with water and it doesn't compete with the water. It competes with the pectin for the water by hydrogen bonding. So C. Andre came back for the 2 points. So C. Andre will get the points. I am so sorry, Joffin, but such is life. So we're on to the next question, guys. And this question says, all of the following are uses of pectin except thickening, gelatining, emulsification, stabilization. All of these are uses of pectin except one of them. Is it thickening, gelatining, emulsification, stabilization? None of the words should be strange. I am seeing B as an answer. I am seeing D. I have no idea why Mikkel is asking me the answer. Miguel says A. Keniva says D. Any other answers? See, Andre says B. See, Andre changed him answer. I wonder why. What was the reason? Any other answers? Anybody want to change their answer? Mikkel says C. Anybody want to change? Javon says C. Anybody wants to change their answer? Anybody else wants the answer? Okay, I assume these are all the answers. So the correct answer is indeed B, and Joffin was the first person to get that correct. The answer is B, as in boy. The answer is gelatining. No, this is a trick question. Just because gelatining can also be used as another word for thickening, meaning you're making something gelatin consistency. However, in this context, gelatining would be the incorrect answer. So gelatin is not a use of pectin. You usually use the word gelatin when you're using gelatin. So you use pectin as a thickener, as an emulsifier, as well as a stabilizer. But gelatin is the exception. So Jophine gets that one correct. On to the next question. So this question is, I'm hoping to remember, and this is 3 points for a reason. What are the typical pH and temperature ranges that are used in conventional pectin extraction? So we talked about the commercial process of pectin extraction and the typical pH range that is used and the typical temperatures that are used for heating. What are those two ranges? C. Andre says 1.5 to 3.0 pH. Miguel says 2.5 to 4. And C. Andre also says 60 to 100 degrees Celsius. Jophine has the same answer as C. Andre. Are there any other answers, people? We all who did pay attention. Are there any other answers? I assume that is a no. The correct answer was from C. Andre, so he got the answer correct. He was the first person to get the correct answer. It is 1.5 to 3 pH because we're using acid, and the temperature range is 60 to 100 degrees Celsius. So C. Andre gets those 3 points, 3 big points. Should I give him a 2? I don't feel like, because I asked you to name 2 things down. I should have said 2 points, but it's okay. I'm going to give you the extra one. So let's go to the next question, shall we? And this question says, which of the following are components of pectin? Is it D, galacturonic acid, L-arabinose, and L-xylose? Is it rhamno-AD, galacturanan, L-galactose, and D-xylose? Is it D-xylose, D-ribulose, and L-galactose? Or is it D-xylose, D-galactose, and D-glucose? And I'm seeing Miguel say D. And Ciandra says A, and Jophine says D. Anybody has a different answer? Miguel says A. Peneva says all of the above. That unfortunately is not an option. All right. So the answer is actually D. So it's D-xylose, D-galactose, and D-glucose. The arabinose is L-arabinose, and you're using D-galacturonic acid. but it's not L-xylose, it's D-xylose, and D-ribulose is not one of the components, right? And it's not L-galactose, it's D-galactose. All right, so we talk about L and D galactose. Can anybody explain what these L and Ds are for? Why is there a differentiation between L glucose, D glucose, L galactose, D galactose? You get an extra point if you tell me why there's a differentiation. Why one name L xylose and one is D xylose? Why is there that system of differentiation? Because the two compounds do exist. All of the compounds on the screen exist, but why is there a differentiation between L and D? Anybody? I give a point, and I'm gonna understand. The orientation of the atoms in the molecule. That is a very good answer. But that is not a very clear answer either. Okay, so C. Andre says isomers, and that's really the word I was looking for. Isomers, they're isomers. Just like when you have R and S, you also have L and D. So especially if you do biochem and you deal with all of those monosaccharides, disaccharides, you deal with amino acids, and so they will have L and D forms. So they're isomers. The OH part is a very good answer because, for example, if I have an amino acid, it's not necessarily the OH, the movement of the OH or the change in position of the OH that makes it L and D. I just asked generally what the L and D means. So essentially they are isomers, so C and Andre gets that point. Can anybody tell me what kind of isomers they are? You get an extra point, of course. I don't ask questions without giving points. What kind of isomers are they? The L and D. Anybody know what type of isomers they are? And can tell me? Nobody? I'm seeing one answer. Nobody else knows these things. We are all chemistry students, you know. I don't understand what's happening. Are we not applying our knowledge? I see somebody says stereoisomers. No, we need to revisit our notes. I see somebody says geometric isomers. No. Somebody said functional. Of all the isomers, functional? If I slap you through the screen. Functional? What are functional isomers, people? This is serious, you know. I don't believe Miguel. I think it's maybe a typo or him copy the wrong thing from Google or something. Can't be. Correct answers is enantiomers. They are optical isomers, mirror images of each other. They are enantiomers. So Jophine gets that point. Functional. Miguel, I joke you make dumb. Yeah, man. I am going to assume that's a joke. Geometric and stereo are not very far guesses, but functionally so far off. All right. So, do we have a next question? I think we have one last question. I believe. Let's go to that question. Joe King Miguel Lefan. Last question. List 5 food items in which pectin can be found. You have 30 seconds to do so. You have 30 seconds to list 5 food items in which pectin can be found. 5 food items. 5, 5. All right. Let me rephrase this question. Oh, never mind. I don't need to rephrase. Because I think Mikkel never interpreted properly. I am not talking about the raw material of pectin. I am talking about something that is produced industrially or commercially that contains pectin, which is why I said food and not fruit. Food items like what you buy. I am seeing, see Andre said tart, jelly, donuts, jam, bread. One of those are off. One of those are off, my friend. Pears, apples, guava, plum, orange. That's not a bad answer, but that's not what I meant. I mean production-wise, commercial foods that are made industrially. Anybody else has any answers? This is literally a giveaway of points. I've been so kind today, just giving away points left, right, and center. Crazy. Crazy stuff. Bread, donuts, jam, jelly, rock cake. Any other answers? Any other answers? They're closed. They're closed. Closed at 4. Huh? Any other answers, guys? Where is everybody else that was answering? Jophine and Keniva and Javon and what's the other name that I'm looking for? Natural Wonders. Not sure who that is, but yeah. But where's everybody else? Are you Googling? Because I'm still waiting on somebody to give away the points too. I assume everybody is on Google. So Javon have jam, jelly, marmalade, donut, and tart. So those are correct. So Javon gets the 3 points. I can't believe you guys let Javon come and get points. Steal away these 3 points from you. So Jams, jellies, marmalade, donut, and tart are all correct. So those are 5 food items in which you can find pectin. So I don't have the total points for today. I will post those so that you can see what the scores were. So you can have a updated scoreboard. But I think either Joffine or Ciandre scored the most points today. So congratulations to you guys. Um, and yeah, I'm supposed to be emailing team members of Team Actonite as well as Joffine regarding prizes, um, and how you're gonna collect them, etc. around this weekend. So look out for that email as well as an update on your club shirts that is coming up. So that's the meeting for today, guys. I will be videoing tomorrow the continuation of the experiment that will be posted either on YouTube or Instagram. You'll get to see it. Most likely YouTube. And then next week we will be doing, we hope to be doing yogurt making. So we're supposed to do ice cream this week, but we had a lot of complications with the liquid nitrogen, which we would be receiving, we would have received Tuesday, but liquid nitrogen boils at about negative 195 degrees Celsius. So if we put it down, even if we put it in a freezer, it will just boil off. And we would not have had it for Thursday, for today. So we can't have any ice cream this week. Next week we'll be doing yogurt making and or wine. Oh God, I forgot to update you guys on the wine, but I will be posting updates later today on the wine making. So we've completed the primary fermentation and we have siphoned the liquid into new bottles. So I will show you guys the updates on that. And hopefully next week we can have some of you come over to SciTech on Thursday so that you can make the yogurt and actually have some of the yogurt as well as some of the wine. So hopefully we can do that for next Thursday, especially for persons who are living on campus or living close by that can come physically. That would be great. So that's it for this week, guys. We will be seeing you next week again. And then, yeah, and then that will be it for February. So I'll see you guys next week.